All right, guys, so in this video, we're going to talk about the three-dimensional coordinate system. You should be pretty familiar with the first dimension, the second dimension. Now we're going to bump it up into the third dimension and just talk about some very, very basic ideas of how it operates. I would encourage you greatly to read your textbook. Some of the stuff that I mentioned is not going to be in there, and there's also going to be some stuff that I don't mention that you'll need to see in the text. So please be sure to take a look at that, especially when it comes to dealing with higher dimensions now. So R1 here, R1, which would be the first dimension, is represented by a line. So if I draw a line here, embedded in that line, you would find points. Okay? R2 would be the second dimension, and that would be a plane. And embedded in a plane, you would have a curve. So something like that could be embedded in a plane. Now, R3 is going to be space. So just for the sake of needing to draw something, our space is going to be a rectangular prism, and embedded in it would then be a surface. So some surface looking like this could be embedded inside of it. And so that's kind of where we're going to be spending most of our time in this section, is in that R3, just getting familiar with the basic idea of how it works. Now, when it comes to the actual coordinate system itself, we'll draw ours using what's called the right-hand rule, where we construct it in such a way that this is the positive x-axis, this is the positive y-axis, and the positive z-axis now. So picture the xy plane being the desk that you have your computer sitting on. The z-axis would run straight up and down from it, okay? Now, I say up and down because what I have drawn here is the positive XYZ axis. The negative sides of these, for example, the negative X would come back this way, the negative Y would come out this way, and the negative Z would come down. Now, I don't know if that helps or hurts the way you view this, but that's kind of how this thing is set up, at least on a two-dimensional screen. Again, please read your book. You'll see it drawn out much nicer with them using a computer. But regardless, when it comes to plotting points now in R3, let's say we want to plot the point 2, 3, 4. Now, we won't be doing this a lot, but I want you to see how it works. So this would be our X, this would be our Y, this would be our Z. So we want to go 2 units in the positive X direction. Notice how my tick marks on the X-axis are going to be parallel to the Y-axis. For the Y, it's going to be a positive 3, so 1, 2, 3, and once again, now those tick marks are parallel with the X-axis. And then for Z, to move up 4 units, these tick marks are going to actually look like this: 1, 2, 3, and 4. So I've moved out a distance of 2 on the X-axis, 3 on the Y-axis, and then I'm going to go up on the Z-axis. So let me sketch in here kind of how this works. Since this is parallel with the y-axis, it's going to run out that way. Parallel to the x-axis, it's going to run out there to where they meet. So on the xy plane, that's where your point would be. But now we need to move up 4 units. So this actually is coming down, and where we intersect right there, that's going to be our point 2, 3, 4. Okay, again, we won't be doing this a lot, but that's just a basic example on how we would do something like this on a two-dimensional board. All right, so now just kind of as a reminder here, when it comes to the XY plane, right, that would be R2, the XY plane. You have the coordinate axes, X and Y, and you have quadrants. Quadrants here would be 1, 2, 3, and 4. When it comes to the R3, your coordinate axes would be the X, the Y, and the Z. And now you would have coordinate planes as well. So let me go ahead and write this out. Coordinate planes. Now, there's 3 of them. There's the case where Z is 0, the case where Y is 0, and the case where X is 0. When Z is 0, that just chops off all of this, leaving us with just the XY plane. So XY plane in this case. When y is 0, it chops off all of this, leaving us with the xz plane. And as you can imagine, when x is 0, that's going to leave us with the yz plane. So again, you still have your coordinate axes. Now you have x, y, and z, but also coordinate planes. Also, we had quadrants, 1, 2, 3, 4. Now, because of how this is broken apart, we have octants. We have, for example, the positive xy, and then you also have the one underneath for the negative z values. And so as you work your way around, you would have 8 of those. This is where, again, looking in the textbook to see that's going to be much easier than what I can draw on the screen. So anyway, there's a nice rundown on kind of how things are going to work in R3 and how the coordinate system is established. I'm going to go ahead and clear the screen now, and we'll take a look at a few examples. Okay, so we'll take a look at a couple specific ideas here, similar to what you would have seen in R2, and fortunately, it's really not going to be difficult to convince you they are what they are. So the first we'll talk about is distance. So the distance between 2 points. Point 1 would be x1, y1, z1, and point 2 sits right there. So the distance between these 2 points is no different whatsoever than it was in R2, because we can still apply the Pythagorean theorem in R3. We're just now going to have an additional component. So we would have the x2 minus x1 squared plus y2 minus y1 squared. Now it's plus z2 minus z1 squared. So it's the same exact idea for distance between 2 points in R3, once again using that Pythagorean idea. And since that holds, we're very fortunate. If you remember, the equation of a circle comes straight from the distance formula. So the equation now, not of a circle, but a sphere, is going to be where we have this guy squared. So if I square both sides, I get rid of the radical, and then all of this underneath. So we'll say equation of a sphere, let's say we have a center at x naught, y naught, z naught, and our radius equals a. If that's the case, then x minus x naught squared plus y minus y naught squared plus z minus z naught squared is going to be equal to our radius squared, so a squared. So distance formula, very similar. Therefore, equation of a sphere, not a circle, very similar. And then the final thing I'll mention is the midpoint formula. And I tell all my algebra classes this really isn't a formula. It's more of just an idea. In R2, we've got x1 plus x2 over 2 and y1 plus y2 over 2. Remember that the reason I say it's not a formula, it's more of something conceptual to understand, just the average, right? If you add up the x's and you divide by 2, that's going to give you the average of where it is. Same with the y. And conveniently, it works the same way with z. z1 plus z2 over 2. And there sits your midpoint formula for R3. This will come into play a little bit later, I believe, but now's just as good a time as any to introduce it.